Okay, now we're going to put it all together. Lewis structures, geometry, and polarity. I have posted a worksheet on D2L for you. You can either print it off and work through these with me, or you can take notes and then try it on your own later and see how well you do. The first structure or molecule we're going to look at, or draw, I should say, and assign geometries to is PBR3. Following the rules for drawing Lewis structures that I've shared with you, we're going to first total the valence electrons for all the atoms in this molecule. And when we do so, we get 28 electrons that we need to distribute. Remember, it's really important to keep track of your electrons. You want to make sure you use them all, but you also want to make sure you don't use more than you actually have. So, to make this look symmetrical, we're going to put phosphorus in the middle, or place it as the central atom. And when I draw the skeletal structure, I use 6 electrons, so I have 20 electrons left, which I will first give an octet to my terminal atoms, the bromines. And after giving the bromines an octet, I have used 18 of those 20 electrons, so I have 2 left. Phosphorus only has 6, so it needs 2 more in order to satisfy the octet rule. So this is our structure for PBR3. Now we're going to assign both electron geometry, and I'm going to start abbreviating that as EG, and we're also going to assign molecular geometry. And I'm going to start referring to this as MG, so I don't have to keep writing that. When we assign electron geometry, we're going to count the electron groups around the central atom. And in this structure, I have 4 electron groups. And let's just remind ourselves what electron groups are. They can be single bonds, double bonds, triple bonds, or lone pairs of electrons. Each of these constitute 1 electron group. Okay, so we have 4 electron groups. I've also posted a handout in the additional handout section under Chapter 10 for you to consult when you are assigning geometries. It also covers hybridization or valence bond theory, which we'll talk about next. So when we have 4 electron groups around that central atom, our geometry is tetrahedral. Now we look at molecular geometry. When assigning molecular geometry, we need to determine how many groups are bonding groups and how many are non-bonding groups. Oops. And these are going to be B and NB from now on. Of those 4 electron groups, 3 of them are bonding and 1 of them is non-bonding. So if you refer to that table, you will find that the molecular geometry is trigonal pyramidal. So, next question, is this molecule polar or nonpolar? And when we want to decide whether a molecule is polar or nonpolar, we have to ask 2 questions. First question, are there polar bonds? And in this case, yes, we do have polar bonds. So remember, a molecule is only polar if it has polar bonds and it's asymmetrical or unsymmetrical or not symmetrical. So second question, do we have symmetry? And another way to look at this is, are all the 4 electron groups around that central atom the same? And in this case, they are not. We have 3 bromines and 1 lone pair. So there is not symmetry, so no to that. So this molecule is polar. Remember, I've also told you that any structure that has a lone pair of electrons on the central atom will be polar. Sorry, shadows barking in the background. Next molecule is N2H2. And we have 2 times 5 plus 2 times 1 here. So we have a total of 12 valence electrons. Now, in this case, we have 2 central atoms. We know hydrogens will only form 1 bond, so the nitrogens have to be central, and the hydrogens terminal. I use 6 electrons, making the skeletal structure, and hydrogens are satisfied with 2 electrons. Remember, they follow the duet rule. However, nitrogen wants an octet. I have only 6 left. Each of the nitrogens needs 4 more. So I'm going to go ahead and give one nitrogen a complete octet, and then I'll give the remaining 2 electrons to the other nitrogen. But this means, though, that we still need to share a pair of electrons between these 2 nitrogen atoms. So we end up with a double bond here. And I'm going to draw this structure again to hopefully somewhat reflect the geometry. Remember the preferred bond, whoops, sorry, that should be an H. Preferred bonding pattern for nitrogen, oops, I don't want yellow, at least not at the moment, is 3 bonds and a lone pair of electrons. So these nitrogens are very happy. So now let's look at the geometries for nitrogen. So again, in this case, we have 2 central atoms. However, the bonding patterns for both nitrogens are the same. So they're going to have the same geometries. So we just need to look at one in order to do this. So let's just look at this nitrogen. Electron geometry, molecular geometry. Okay. Count the bonding group, or the electron groups around that nitrogen. We have 3 electron groups. 3 electron groups corresponds to trigonal planar geometry. Now we'll look at electron geometry. How many of those 3 electron groups are bonding and how many are non-bonding? We have 2 bonding groups and 1 non-bonding group. So this corresponds to a bent geometry. Is this molecule polar? Does it have polar bonds? Yes. Is it symmetrical? No. And we, in fact, have permanent dipoles going in those directions. So this is a polar molecule. Lone pairs on the central atom. Next up, CH3OH. And you've seen this type of molecule before when we looked at combustion reactions. This is an organic compound, and it's in a class called alcohols. Remember, we discussed that this OH group is not the same or does not equal OH minus, which is, of course, the hydroxide ion. We have 4 plus 3 times 1 plus 6 plus 1 more for that other hydrogen. So we have a total of 14 valence electrons to distribute here. The formula tells me that I have 3 hydrogens bonded to this carbon, 1 oxygen bonded to that carbon, and then the hydrogen bonded to that oxygen. And when I draw this skeletal structure, I use 10 electrons. So I have 4 left. And oxygen is the only atom in the structure that does not have an octet or a duet for the hydrogens. So those 4 electrons go to oxygen. And while we consider carbon to be the central atom, we can assign geometries to both carbon and oxygen. So we're going to look at both. So for carbon, electron geometry, we have 4 electron groups, which corresponds to tetrahedral geometry. And molecular geometry will be the same because they're all bonding groups. In other words, we don't have any lone pairs on the central atom or that carbon, so that will be the same geometry. Remember, when we have lone pairs on the central atom, molecular geometry will be different than the electron geometry. Now we can also look at the geometry about oxygen. Electron groups, oxygen has 4, 2 bonds, 2 lone pairs, so 4 electron groups. So electron geometry is also tetrahedral. However, our molecular geometry, we have 2 bonding and 2 non-bonding groups. So the geometry about oxygen is bent. So I could redraw this to reflect that bent structure. Also means we have a dipole here. So when it comes to polarity, yes, we have polar bonds, and the 4 atoms bonded to carbon are not the same. So this is asymmetric, plus we have that bent structure in this molecule. So we have a polar molecule. Now for these alcohols, the small ones, let's say up to about 6 carbons, will be polar. However, as the carbon chain grows, polarity decreases until it's non-existent. Now we're going to look at an ion, NO2 minus, one of our apolyatomic ion, I should say. 5 plus 2 times 6 plus 1 electron for that negative charge, gives us a total of 18 valence electrons. Nitrogen central, I use 4, 14 left, and I'll give my terminal atoms an octet first. using up 12 of those electrons, and I finally give nitrogen the remaining 2. However, nitrogen is still lacking 2 electrons, so that means that one of those oxygens must share a pair of electrons with nitrogen. Both oxygens are capable of doing so, and so if you recall what happens then, we have resonance. So there are 2 structures. And then, of course, we need brackets around that ion. The other structure, the double bond, is between the nitrogen and the other oxygen. So 2 resonance structures for this polyatomic ion. This is an ion. It is charged, so we will not be assigning polarity to that. However, we can assign geometry, electron geometry. We have 1, 2, 3 electron groups, which corresponds to trigonal planar geometry. Excuse me, I got sidetracked here. Molecular geometry then, of those 3 groups, 2 are bonding and 1 is non-bonding. So we have a bent structure. Next molecule we have is C2H4. 2 times, oops, what happened? All right, what's going on here? My pen doesn't seem to be working at the moment. There we go. Plus 4 times 1 gives us 12 electrons. Again, in this case, we have 2 central atoms, carbons. Each of those carbons has 2 hydrogens attached. And when I make the skeletal structure, I use 10 electrons. Only 2 electrons left, and both of those carbons needs 2 more electrons. So I'm going to give those electrons to one of the carbons, and then those will be shared between the 2 carbon atoms. Okay. Electron geometry. Let me redraw my structure here. Since both of the bonding patterns for those carbon atoms are equivalent, we can just look at one of them. So we have 3 electron groups, which corresponds to trigonal planar. In molecular geometry, we have 3 bonding groups and 0 non-bonding groups. So molecular geometry is also trigonal planar. What about polarity? Is this molecule symmetrical? Yes. We have polar bonds, but we have symmetry. So this is a non-polar molecule. Next is BSF, boron. What do you remember about boron? Think about that. 3 bonds only, 3 valence electrons. When we total our valence electrons, we have 16. Boron is going to be central. It doesn't matter which side you put the S and the F on. Use 4 electrons, have 12 left, and we're going to give the terminal atoms an octet first, using up all of our electrons. Now, that means that somebody's got to share a pair of electrons with boron. Will it be fluorine or sulfur? Remember, halogens form only one bond unless they're in a polyatomic ion. So fluorine will not double bond with boron, but sulfur will. So we have S, double bond B, F, and this is our structure. Electron geometry. How many bonding groups? 2. Or 2, I meant electron groups. 2 electron groups, which corresponds to linear geometry. Molecular geometry. The 2 electron groups are bonding groups. We have 0 non-bonding groups. So our molecular geometry is also linear. Do we have polar bonds? Yes, we do. Do we have symmetry in this molecule? No, we don't. 2 different atoms are bonded to that boron. So we have a polar molecule. HBr, 1 plus 7, 8 electrons. And I'm not going to go through the steps on this one. This is what that Lewis structure looks like. We don't really have a central atom, so to speak, but a binary acid, and it is linear. There's no way for it to be anything otherwise for both electron and molecular geometry. Is it polar? Yes. We have a permanent dipole. Bromine is far more electronegative than hydrogen. C2H3O5, I'm sorry, not O5, C3H5OH. Ethanol, you've also seen this one. I'm just going to, on this one, draw the structure for you, and then I'd like you to go ahead and assign the geometries. This formula tells me I've got 2 carbons bonded together with 5 hydrogens attached to them, and then an OH. And this oxygen has 2 lone pairs. So I would like you to assign geometries for carbon, both electron and molecular, and for oxygen. Both carbons are equivalent in that they each have 4 single bonds, so you only have to look at one of them. And then, of course, we have the oxygen atom that also has geometry associated with it. N2F4, 2 times 5 plus 4 times 7 gives us 28. Once again, nitrogens will be central, and the fluorine atoms terminal, because they'll only make one bond. I use 10 electrons in my skeletal structure, so I have 18 left. Give those terminal atoms an octet first. In doing so, I've used, wait, did I have the wrong total there? Yeah, I did. Sorry about that. This should have been 38. And this is 28, because I just used 24. So I only have 4 left. So I'm going to give each of those nitrogens a lone pair, and now they have satisfied the octet rule. So again, we have 2 central atoms. They're equivalent, so all we have to do is look at one of them for assigning electron geometry. We have 1, 2, 3, 4 electron groups, which corresponds to tetrahedral geometry. And when it comes to molecular geometry, 3 of those groups are bonding, and we have 1 non-bonding group. So we have a trigonal pyramid, or pyramidal molecular geometry. We have polar bonds. We have those lone pairs on the central atom. So this is a polar molecule. We have one more structure on this worksheet, SF6. 6 plus 6 times 7 gives us 48 electrons to distribute. Sulfur is central. Remember that sulfur has an empty d subshell and therefore can accommodate an expanded octet. And in our upcoming topic of valence bond theory, we'll look at an explanation of how this might occur. But for now, we're sticking to geometries and polarity. So using that, or drawing that skeletal structure, I used 12 electrons, 36 left, and when I give the fluorine atoms an octet, I will use up the remaining electrons, and everybody's happy. Okay, so electron geometry. How many electrons around that central, or how many electron groups around that central atom? There are 6. And this corresponds to octahedral geometry. There are no lone pairs. There are 6 bonding groups and 0 non-bonding groups. So molecular geometry is the same. Is this molecule polar? It has polar bonds. However, all the atoms bonded to the central atom are the same. So this is a non-polar molecule. And that's it for the worksheet. Valence bond theory will be the next topic.